Imagine a Roman city at dawn. The square is already awake. Sandals scrape stone. Clay jars knock against tired hips. A fountain sits in the middle of the street like a promise that has not yet been kept. The basin is dry, and somewhere beyond the walls, beyond the fields, beyond the low blue hills, water is moving toward the city without a pump, without a wheel, without a piston, without a single engine in the modern sense. That is the Roman trick. Not magic, not myth, precision. We tend to remember Roman aqueducts as arches against the sky because arches photograph well. But the most important part of the system was the part people rarely saw. Most of the line usually ran underground, hidden in trenches, tunnels, and covered channels. The monument was only the visible fragment. The machine was the root itself. Over centuries, Rome built 11 aqueducts to feed its capital, and the combined length of those lines ran for hundreds of kilometers. Only a small portion crossed valleys on arches. The rest disappeared into the land, which is exactly where Roman engineers wanted it. Why go to that trouble? Because wells and rainwater could support a town. They could not easily support a metropolis of baths, fountains, workshops, latrines, gardens, and dense neighborhoods. Roman urban life demanded more than survival. It demanded reliability. Public fountains had to run. Bath complexes had to fill. Streets, drains, and public spaces had to be supplied again and again, every day, in every season that the source could endure. So the problem was not simply how to find water. The problem was how to make water arrive predictably in volume, over distance, with no pump waiting at the end to save a bad design. That meant the first job was not building, it was choosing. Roman engineers preferred good sources, often springs, because a city could suffer from bad water in slow, relentless ways. The search begins in the hills. A spring emerges from rock. The engineer kneels beside it. He looks for clarity, steadiness, taste, smell, and volume. The city is not yet present, but it is already in the calculation. Every bath, every basin, every household grant, every public demand is hidden in that quiet pool. If the source is wrong, the line is wrong. And if the line is wrong, the city will pay for the mistake in stone, in labor, and eventually in thirst. Once a source is chosen, the real Roman genius appears: surveying. Ancient writers describe the corribits, a long, leveling instrument fitted with plumb lines and, when the wind disturbed them, a shallow water trough to confirm true level. This is not glamorous work, but it is the heart of everything that follows. The line must always fall, never rise. Yet it cannot fall too fast. Fast water can damage masonry, destabilize flow, and complicate the system. Slow water can lose energy, collect silt, and fail to deliver as intended. Roman engineers were not working with electric pumps that could rescue bad geometry. They had gravity alone, and gravity is unforgiving. Once the route is set, the future of the city is already half written. That future usually stayed underground. The famous arches were the exception, not the rule. Most aqueduct channels were built as covered trenches or tunnels following the contours of the landscape. Hills were skirted when possible. If the line had to pass through rock, crews dug shafts and attacked the tunnel from multiple points. The labor was brutal. Picks, baskets, lamps, dust, mud, stale air, and the constant risk that one mistaken direction would turn months of work into a dead end. When two tunnel teams finally broke through and met correctly, it was not only a construction success, it was proof that the invisible mathematics of the route had held. Then came the channel itself, the spacus, the narrow stone throat through which the city would eventually drink. It had to be lined, smoothed, sealed, and protected from sunlight, contamination, and damage. Roman builders roofed these channels because water was not supposed to be exposed if it did not need to be exposed. This is one reason the surviving arcades can mislead us. They make the system look theatrical. In truth, Roman water engineering was often modest in appearance and relentless in discipline. A viewer might admire the bridge, the engineer admired the gradient. And yet sometimes the land forced the line into view. Valleys had to be crossed somehow. In some places the answer was an arcade, a bridge carrying the channel across open air. The Pont de Gare, part of the Aqueduct to Nîmes, remains the most famous example because it reveals in stone what the rest of the system tried to conceal. That line ran for about 50 kilometers, and the average fall from source to city was astonishingly slight. The bridge is not just beautiful, it is evidence of confidence. Roman builders trusted that if the route had been measured properly, the water would keep moving with no help from any machine except the slope they had imposed on the landscape. But arches were not always the answer. Some valleys were too deep, too wide, or too expensive for monumental bridge work. In those places, Roman engineers sometimes used what we call an inverted siphon. The principle is simple enough to explain and difficult enough to execute. Water entered a header tank, dropped down one side of a valley into a closed pressure line, crossed the low point, and rose again to a receiving tank on the far side, according to the principle of communicating vessels. The danger was pressure. In an open channel, water glides. In a pressure line, water pushes. Joints matter. Materials matter. The slope of the pipes matters. A weak seam can turn elegant design into sprayed loss, repair work, or collapse. Roman engineers used lead, ceramic, and stone in different contexts, always wrestling with the same problem: how to force water through a dangerous place and return it safely to open flow. By the time the line reached the city, the problem changed again. Long-distance conveyance was only half the job. Urban distribution required a new level of control. Water entered a castellum, a distribution tank or basin, at a high point. There, the line became a network. Ancient descriptions and archaeological remains show a logic of division. Water directed toward public fountains, toward baths, toward other users, and in some cases toward private houses under formal grant. At Pompeii, the Castellum Aquae stood at the city's high point and split supply into major outlets. The structure itself was not grand on the scale of a bridge, but it was in some ways more revealing. The aqueduct was not merely delivering water, it was organizing society. That is the point where Roman engineering becomes Roman government. Once water enters the city, it becomes law, privilege, maintenance, revenue, and political theater. Public fountains matter because they are visible and social. Anyone can see them run. Baths matter because they transform water into identity. A Roman bath is not just a place to wash. It is a machine of culture, business, routine, hierarchy, and pleasure. Latrines and drains matter because flowing water also supports sanitation. Private house connections matter because they convert civic abundance into personal prestige. The water does not stop being hydraulic, but it becomes unmistakably political. Roman writers understood this. Vitruvius describes the logic of distribution from a city reservoir with a triple arrangement that protected public use. Frontinus, writing as a water administrator, recorded the practical realities of the system: the measurements, the grants, the policing, the maintenance, and the theft. Because yes, where water flows, someone eventually tries to steal it. Illegal taps appeared in Roman systems just as illegal taps appear in modern ones. And because it was managed, it had to be maintained constantly. This is one of the least glamorous and most revealing truths about Roman aqueducts. They were not miracles achieved once. They were systems kept alive by inspection, cleaning, patching, scraping, walking, and repairing. Channels collected carbonate deposits, cracks opened in masonry, vegetation, shifting ground, storm damage, and simple wear all threatened the line. A single weak point could compromise supply far downstream. Maintenance crews walked the routes, checked seams, cleared deposits, and protected the corridor. This is also where the human cost comes into view. We like to stand before a surviving arcade and feel wonder, and wonder is deserved. But wonder should not erase labor. Every fountain in a Roman square reaches back to a quarry, a trench, a shaft, a scaffold, a workshop, and a maintenance path. Men cut the stone, men surveyed the route, men hauled blocks in dust and heat. Men crawled through tunnel headings on bad air and weak light. Some were skilled specialists. Some were ordinary workers. Some were enslaved. Some were officials. All were part of the price of precision. Roman water looks effortless only after the labor has been hidden underground, and still, when the system worked, the effect must have felt almost supernatural. Imagine the first arrival of water in a city that has invested years in distance, masonry, and faith. First, the sound changes. Then the basin darkens. Then a bronze mouth spits, surges, and finally pours. Suddenly, a public square has been transformed. Labor that was invisible becomes visible in an instant. The people do not see the survey line in the hills, the tunnel alignment, the pressure calculation, the basin logic, or the maintenance law. They see abundance. They hear authority. They understand that the state has reached beyond the horizon and dragged a spring into their street. That is why aqueducts mattered so deeply to Roman power. They were practical, yes, but they also performed civilization. They announced that Rome could discipline terrain, labor, and water at scale. A city fed by an aqueduct was not merely surviving, it was participating in a system larger than itself. Fountains, baths, and overflow were evidence of order. A running line signaled competence, a dry basin signaled danger, and danger never disappeared. Earthquakes could fracture channels, floods could batter river crossings, war could turn a water line into a target. An aqueduct was strategically vulnerable precisely because a city depended on it. Cut the line, and the city hears the change before it fully understands the cause. The fountain weakens. The bath quiets. The crowd thickens at the well. Old labor returns overnight. That contrast reveals how profoundly the aqueduct had altered daily life. Once a city becomes accustomed to constant flow, the loss of flow is not only physical, it is psychological. Yet many Roman lines endured astonishingly well. Some fell into ruin, some were dismantled for stone, some survived in fragments. A few continued to influence later water systems or remained partly in use across long stretches of history. Surviving monuments like the Pont de Garde endure because Roman builders married elegant form to disciplined function. The archaeological remains of places like Pompeii endure because catastrophe froze the urban system in place, preserving the logic of distribution almost like a diagram cut into the city itself. The ruins do not merely say that Rome built large things. They say Rome understood flow. That may be the clearest way to put it. Rome did not defeat gravity. Rome learned to work inside gravity so precisely that gravity itself became infrastructure. A spring higher than the city, a route that never accidentally rose, tunnels where hills resisted, arches where valleys opened, pressure lines where arches failed, distribution tanks where flow became policy, fountains where policy became daily life, drains where surplus became sanitation, maintenance where triumph became routine. This is how a city received water without pumps, and perhaps that is why the remains still affect us. Stand beneath an arcade, walk beside a buried line, lean over a silent channel. The grandeur is real, but the deeper achievement is quieter. The real Roman machine was the landscape after it had been measured, cut, lined, protected, and disciplined into obedience. Water then did what water had always done. It moved downhill. The miracle was not that the Romans broke the laws of nature. The miracle was that they understood those laws well enough to build a civilization out of almost invisible compliance. So the next time you see a Roman aqueduct, do not only look up at the arches, look outward. Imagine the source in the hills, the surveyor with his leveling beam, the tunnel laborer in lamp smoke, the mason trimming the channel, the clerk recording the grant, the woman waiting by the basin, the bath rising into steam, the drain carrying excess away, the inspector walking the route, the city listening to the sound of water as proof that the system still holds. That sound is the true monument, not the stone, not the arch, not even the fountain itself. The sound of water arriving where it should not be possible for water to arrive. Without pumps, without engines, with gravity alone, turned by Roman hands into the bloodstream of a city.